as part of a workshop that we already provided in Perth in October, and this March at the PDAC. And because it takes a lot of time to compile that much material, put everything together, I thought it would be a good idea to do a summary of the slides and to present it to a wider audience through the TGDG. So as an introduction, the goal of this presentation is not to show an exhaustive review of what VMS deposits are and structural controls are, but rather to share experiences of what we think is important on the primary and post-deposition structural controls, and to focus on their impact both for exploration and understanding the deposit geometry and delineation. So what are volcanogenic massive sulfide deposits? Oh, sorry, there's a little bit of noise. So what are VMS deposits? It's a type of deposit that's interpreted to be syngenetic, meaning that they're deposited during the deposition of volcanic units at the base of the seafloor. So there are examples of fossil examples of deposits that are currently forming on the seafloor that are called the seafloor massive sulfide deposits. And they're major sources of both base metals and precious metals like silver and gold. So there's an overall model for the formation of VMS deposits. The important points are the presence of a magma reservoir deep or not too deep in the crust, not as a source of metals, but as a source of heat. And then you have on the seafloor a system of fractures along which fluids are going to circulate, and the heat will allow the formation of hydrothermal cells, and the heated fluids will leach metals from volcanic rocks, go up and deposit them when they arrive close to the seafloor due to the temperature drop and interaction with cool fluids. So that's the overall conceptual model. In terms of geodynamic setting, very quickly, overall, the VMS deposits form in plate margins, can be convergent, can be divergent. So it can be arcs, rifting zones, and the majority of the deposits are not preserved due to plate recycling. A little bit more on that, the vast majority of VMS or SMS deposits that currently form on the seafloor are on the oceanic crust alongside rifts. And as you know, most of this crust is recycled, so the vast majority of the deposits that form will be recycled and will never make it on the continent. So that raises an important point, is that to preserve a deposit, you need to have post-deformation events that will bring it up to surface. This is generally a contraction event, and this will affect the geometry of your deposit to be able to bring it to surface. So in terms of overall concept of structures, for the formation of the deposits themselves in the VMS environment, there's two scales of structures that are important. The first one is, how do you bring magma close enough to surface to form a reservoir for the heat? The conceptual model that you can see here on the right, you have partial melting of the mantle or of the crust, and magma going up through conduits. The reality is that magma doesn't go up anywhere. It needs a structure, it needs a conduit to go up. So finding this type of structures at a large scale, at a province scale, this is where you're going to find your VMS districts. In a more focused space, once you have your magma that's in place within the crust, you'll need structures to drive down fluids to form hydrothermal cells and structures to drive it up. An important point is that when you leach metals and elements from the volcanic rocks, when the fluids are going up, they'll form a zone of silicification that you can see represented right here. What this silicification means is that it's going to form an aquiclude. So it's going to prevent fluids from rising again. So if you don't have an active fault system, that's it, the fluids won't be able to go up. So with this silicification forming, the only way for the fluids to go up is to go along active fractures that are still open and that remain open due to movement. So on the large scale, how to find VMS prospective terrains? The idea of finding these large transcriptural faults that will bring the magma up is really interesting, but when you look at deformed belts, that's harder. The best proxy is to find the location of submarine volcanic and intrusive oceanic and arc rocks. The reason for that is that because these rocks are from magma that have gone up, that's the best way to localize these old transcrustal faults, even if they are now hard to directly detect. On a smaller scale, these synvolcanic faults, how can they be, or what's their impact on the location of deposits? Here's an example of current seafloor deposit to illustrate that. So you have the Brothers volcanoes that are located alongside a major plate boundary that's convergent. This is an arc. And when you look at the actual volcano where the currently forming seafloor mineralization, that's within the volcano and at the boundary here of the sorry, losing my word, of the caldera. At the boundary of the caldera, so the caldera is fault bounded. You have some seafloor forming right here because you have synvolcanic faults that are active at the right now, and also on the top of recent magmatic eruption. So same thing, you have an active conduit that was used by rising magmas and lava, and you're able to have hydrothermal fluids using the same conduit to form seafloor mineralization. So again, the location of the deposits at different scales is constrained by the presence and the location of these both translithospheric faults and more focused synvolcanic faults. So for this reason, understanding the volcanic architecture, the primary volcanic architecture of your VMS district is extremely important, and it's going to be more predictive about the location of VMS deposits. So here's the example of the Okuroku district in Japan, where clearly you have the vast majority of the known deposits that are located within mapped calderas. If you know where the calderas are, you know where to search. You're more likely to find them at the boundary or along faults within the caldera. So knowing your volcanic architecture is a really good proxy to targeting and finding deposits. The issue is that this is not an easy job to find or to understand the primary architecture of a volcanic sequence that has been highly deformed, especially mapping these synvolcanic faults. But they're proxies. Even if with deformation you're not able to see the faults anymore, they have been overprinted, obliterated, they're proxies. So because they are synvolcanic faults, all sorts of things will circulate along them, not just hydrothermal fluids, but also magmas. So looking at synvolcanic dikes, you're able to see where there are higher concentration of these synvolcanic dikes. You're able to follow primary synvolcanic faults. Same thing with alteration zones. Again, the alteration hydrothermal fluids, they're concentrated or they're focused along these synvolcanic faults. So being able to map spatially the distribution of these regional hydrothermal alteration, you're able to constrain where your synvolcanic faults were. And here's an example of a nice outcrop saying both both features occurring. You have a synvolcanic dike. How do I know it's a synvolcanic dike? It's intruding volcanoclastic rocks, and you see the contact of the dike is all waving. So it's not a straight line, sharp line, because it was intruded in semi-consolidated volcanosedimentary rocks. And at the margin of the dike, you have a silicification that's affecting the wall rocks. So these white patches right here that you see are along the contact of the dike and pervasively affecting the wall rocks and progressively diminishing in intensity. So here, this is a really good example of what was very likely a synvolcanic fault. That's, well, hard to map as a fault as of today. There's no breccia, there's no gouge anymore because of the metamorphism and deformation. Here's an example, similar example at a different scale. This is the Bergslagen district in Scandinavia, where you have right here in brown, you have one horizon of volcanic quiet. So this is a time where there was less volcanism, less lava flows depositing, and along it you have an entire series of VMS deposits and related occurrences. along these horizons. And when you look at the footwall of this district, you see a vast volume of rock that's affected by garnet alteration. So you have the volcanic pile that has a high volume of garnet alteration. That's the effect of metamorphism of a large regional hydrothermal system. So when you look at where this garnet alteration is located, so that's the gray with green dots within this more beige colored volcanic unit, you see it's right in the footwall of your VMS system, and it's centered in the distribution of your VMS system. So you're able to see, okay, this is where the fluids went up, even after deformation, even after not being able to see these faults anymore, you can see where the fluids went up, and you can map your initial synvolcanic fault. Another way to map synvolcanic faults, again, with the reconstruction or the understanding of your volcanic architecture, is to look for abrupt changes in volcanic deposits, types, and thickness. One example is volcanoclastic rock that will very abruptly change in terms of thickness along a fault. One side of the fault is very thick, the other it's very thin. This is not a syn deformation process. It's very likely to be syn deposition, so the effect of active faults during deposition, they'll control the thickness. Same thing with coherent flows. If you have more coherent flows along a fault, it's very likely the coherent flows use this fault to arrive at surface. And seeing the concentration of coherent flows, finding the volcanic centers, you're able to see where your initial synvolcanic faults were located. One thing to be careful about is that these faults tend to be inverted during compression event, which can give contradicting information with both normal and reverse displacement. So the 3D reconstruction of the volcanic architecture is a really good tool to identify these thickness changes and the location of synvolcanic faults. So now that we've seen a little bit more the regional or district scale context and how to find where these deposits can be located, let's have a look at the overall VMS conceptual geometry and what are the impacts of synvolcanic structural framework for their geometry. So starting with the conceptual geometry, that's a figure I think most of us have seen and we've seen at university of the ideal VMS deposit with forming at the seafloor, within yellow the massive sulfide zones that's grading from higher temperature chalcopyrite rich ore to sphalerite galena, and then sphalerite galena barite at the top to a lower temperature. Often with an exolite or chert horizon at the top, and a discordant stockwork zone, that's the feeder zone where the fluids, hydrothermal fluids are arriving. That's often associated with chlorite alteration, higher temperature iron-rich chlorite alteration, a lot of chalcopyrite, pyrite, and a halo around this pipe. That's going to be chlorite, sericite alteration, so lower temperature. So we have the metallization, we have the alteration, and this is the overall general conceptual geometry, but the reality is often a lot more complex. However, it's still possible to observe this geometry in deformed deposits. I give 3 examples here from a paper from Lorge in 1992, where you have, right here, the massive mineralization that's at the top, which is more zinc and lead enriched, and a copper zone that's at the bottom. Here, same thing, you have your zinc copper sulfides, massive sulfide zone, and in the footwall you have this stringer pyrite chalcopyrite zone. So even if the geometry has been deformed, we find the same conceptual relationship than we had in a conceptual model. Same thing here, you have zinc-rich massive sulfides, and in the footwall chalcopyrite, but more interestingly in this cross-section for this deposit is that you have 2 stacked or stratigraphically stacked deposit. You have a first, do I have a pointer? Yeah, that's gonna be easier like that. You have a first horizon right here, black of massive sulfide with a stringer zone at the bottom. and under it, in its footwall, another horizon of massive sulfide with another zone of stringer. So two stacked, stratigraphically stacked VMS. So already a little bit of more complexity relative to the conceptual model. An important point is that this conceptual model is not observed only in ancient and fossil VMS systems. It's also the same thing that we observe in current SMS system currently forming at the bottom of the ocean. Here is an example where you have some drill holes that show the presence of the massive sulfides at the top and grading into sulfide feeder zone at the bottom. So the exact same geometry, again, with stacked lenses that we can observe right here. So exact same geometry in the current systems compared to the ancient systems we exploit as VMS deposits. An important point is that, again, this is the general model. There's a lot of more complexity in terms of geometry and deposit formation. The one deposit formation we've seen is the massive sulfide forming at the bottom of the seafloor. It's possible for them to form as a subsea floor replacement. So the hydrothermal fluid never reaches the bottom of the ocean. It's going to go pervasively into volcanoclastic or sedimentary rocks and form there, so as semi-massive sulfides. Or you have brine pools. This is an example of a deep brine pool in the Red Sea, where the hydrothermal fluids, instead of depositing right where they're expelled in the ocean, will go in the water column and will resediment a little bit further in topographic low zones. So again, when you imagine that you have this variety of geometries and then you put deformation on top of that, that can lead to very complex end geometries. So what does it look like? Massive sulfide mineralization, when it's not too deformed, you can see really nice primary textures like sulfide breccias. You even have potential of turbidites. In drill core, here's an example of massive sulfides at the Laron deposit. This is the top of the zone, the massive sulfide conformable zone. And at the bottom, you have the stringer zone. Here, an example from the Lalor deposit, which is copper enriched. Interesting point to see as well is the alteration zones in drill core. This is the same rock, so both from the K deposit. These two photos are from rhyolite. On the left, this is the rhyolite affected by sericite alteration. On the right, by chlorite alteration. I want to emphasize that when you're working in VMS deposits, the mineralogy doesn't tell you what rock it is. Someone would say, oh, this is a mafic schist. No, this is a rhyolite. But due to the intensity of the alteration, all the quartz has been, or the vast majority of the quartz has been leached, and we're left with a lot of chlorite, which is not a normal mineral for felsic rocks. Here are examples of outcrops of VMS mineralization, where you have the massive sulfide here on the left, and right below it, the stringer zone. So this is from VMS ore at Matagami. Another example, this one from the Lalor deposit, where you have the exact same thing, the massive sulfide, and right below it, the stringer zone. So again, copper, zinc, lead enriched at the top, and copper rich at the bottom in the stringer zone. Sorry, you wanted to, oh, okay. And two examples of alteration, sericite alteration and chlorite alteration underground. Again, on the right, this is the MacLeod deposit. And if I remember correctly, this is also a felsic rock, completely chlorite altered. I'm not 100% sure on this one. I don't remember clearly, but yeah. So I've been talking a lot. I think it's time for you a little bit of exercise for you and your time to talk. I just wanted to show a really good example of how it's possible in one drill hole to identify the geometry of a VMS deposit. So the question I have here is, looking at this drill hole intersection right here, which way is the stratigraphic top and why? Do you think so? Remembering about the geometry of the VMS system, the metal zonation. Yeah. So yeah, the way up, stratigraphic top, is at the top of the drill hole. The reason for that is that it's going to be zinc enriched, the zinc decreasing downward, and the bottom is copper enriched with the copper decreasing upward. So we can find, even despite all the deformation, it's possible to reconstruct what was the the geometry, initial geometry of a VMS deposit, understand the stratigraphic, the Younging direction, just from one drill hole. This can be a really powerful tool when trying to understand the structural context of a deposit. But even before that, we have to keep in mind that these deposits already have complex geometries even before deformation. This is an example of a currently forming SMS deposit. And you have the topography on top of which has been draped electromagnetic conductive areas. So basically, the summary here is that these little mounds with the red color, this is the sulfide mineralization. And as you can see, this is not a simple cone at the bottom of the ocean like the general model or the conceptual model wants to sell us. This is a strongly structurally controlled formation with trends that can be probably interpreted as synvolcanic faults along which the hydrothermal fluid are expelled into the water column. So the lens and pipe geometry is a generalization, and individual deposits geometry will vary significantly. It's something we have to remember. With the deformation, you'll tend to lose this initial geometry, but you still have ways to reconstruct it and to understand it. Here's an example where you can see or infer the location of the synvolcanic faults looking at the distribution of metals. So here on the right, we're looking at the bottom of a massive sulfide lens. And when you look at copper, you can see alignments or trends of copper, so high temperature mineralization that probably represents synvolcanic faults. Again, here, other lenses where you see the same thing, and the copper over iron ratio, which really shows really well these different trends that have been preserved despite all the deformation. I want to emphasize again these synvolcanic faults. As we've seen, they're important to map for understanding where the deposits can be located. They control the formation, the location, and the geometry of these deposits. The issue being that they're obscured by subsequent deformation. We've seen that there are proxies like volcanic and intrusive rocks, changes in the thickness of volcanosedimentary deposits, for example, that can be used. But we have to be careful when identifying these faults. In highly deformed rocks at grid schist metamorphic facies or above, the undeformed brittle faults that we observe in the field are really unlikely to be synvolcanic faults. And this is an error that we often see, is people trying to map these synvolcanic faults. And here's an example right here. So these ones are not, I don't think they're mapped as synvolcanic faults. But in a case like that, so this is just an illustration, when you have strongly transposed units that are parallel to a structural trend, and you have faults that are perpendicular to it, look brittle, they offset the deposits, have a look at it. But if they are not affected by the deformation, if they cross-cut the deformation, unlikely to be in synvolcanic fault, and this is unlikely to help you or to be a good proxy for finding VMS deposits. So establishing the timing of events and cross-cutting relationship is critical when exploring for in a VMS camp. It's not just for orogenic gold deposits, it's also valid for VMS exploration. With a little caveat, is that synvolcanic faults can be inverted during deformation. This is an example from the Rio Tinto deposit in Spain, where you have this current geometry of faults that have acted as a reverse fault, or the last recorded event is a reverse fault, along which you have your alteration, your massive sulfide mineralization. But when you look at the actual offset, so not the recorded deformation along the fault plane, but the actual offset, you still have evidences of normal displacement that's stronger than the reverse displacement. So these faults initially were normal faults along which hydrothermal fluid has circulated that have been inverted during the compression. So initially they had a normal movement. They're used for the formation of the VMS deposit. And when you invert, so instead of extension, you use the same direction for compression, you reuse this fault as a reverse fault, and you end up having this confusing relationship. So in this case, you can look for your reverse fault, because you can infer there are synvolcanic faults that have been inverted, as a proxy for the targeting for VMS deposits. And there's a really good paper, I think it was in the Skellefteå district in Sweden, where they used current reverse fault and measured the relationship they had with VMS deposits. And there was a special relationship between reverse faults and VMS deposit, the interpretation being that they are inverted faults. And there was also a really good correlation in the shape of the VMS deposits with the orientation of the foliation that was overprinting them. So again, it's a complex history. There is synvolcanic controls, but it's overprinted by deformation that will affect and completely change its geometry, which leads us to the effect of deformation on VMS deposits. So right now we have seen the effect of synvolcanic structural controls. The second part of the presentation is about deformation and the effect of deformation. The first important effect of deformation and contraction on the VMS deposit, that would be folding, very common. You have a few examples of folded VMS deposits on the right. And what's going to generally happen with enough deformation is that you'll have thickening of the hinges of the folds, and you have thinning along the limbs of the folds. And you'll have this geometry that we observe right here with very thick mineralization at the hinges and something that's a lot thinner and hard to follow on the limbs. This can make the difference between a deposit not being economical and becoming economical because it's been thickened within the fold hinges. Again, the geometry of the ore has changed. Now the plunge of the ore is the plunge of the fold. So the main control on the geometry of the deposit is not syn sedimentary or syn volcanic structural controls. It's the syn deformation later structural controls. So how do we identify folding in a VMS deposit? We've seen it's possible in just one drill hole to see the stratigraphic Younging direction. You can use that at the scale of a deposit to map folding. Here's an example of another drill hole right here on the right. And if you observe just the zinc and copper mineralization right here, you see zinc is on this lens here in gray. You see zinc is decreasing downward, copper is increasing downward. So that means the Younging direction is at the top. But this lens right at the bottom, that's the other way around. Copper is decreasing downward and zinc is decreasing downward. So you have the Younging direction is at the bottom. You very likely have overturned fold in between these two intersections. So with just one drill, you can start to infer geometry and the effect of deformation on the geometry of the deposit. So very often, even with a relatively strong deformation, you'll still have this metal zonation. But with extreme example of deformation, you can sometimes completely obliterate it, and you won't find this zoning anymore. An important point is that at the end of strongly folding refolding of deposits and multi-phase folding, the final geometry of the deposit is not anymore affected or dominated by the initial geometry, but it's dominated by the folding geometry. So here's an example of the chisel deposit, where the final geometry and the overall geometry of the deposit, as shown in this stereonet, is completely controlled by the folding. Here, two episodes of folding, the F1-2 and the F3 fold. Another example of the effect of deformation on VMS deposits, that's transposition. So what is transposition? I give an example here on sedimentary rocks, but you can imagine the exact same thing is going to happen to a VMS deposit. On the left, you have the least deformed rock. On the right, you have the most deformed rock. They look pretty similar. What happens is that you have a sedimentary well-bedded rock. You start to overprint it with foliation. And with the more intense deformation, the foliation will be more intense, closely spaced, and the bedding will progressively rotate subparallel to your foliation. So you end up with the most deformed rock looking like a nicely bedded rock. The exact same thing can happen with a VMS deposit, and very often the bedding or the fabric you'll see in a VMS deposit within the sulfides is related to deformation. This is not scene sedimentary or scene deposition textures. This is very likely to be scene deformation textures. Here's an example in the Doyon-Bousquet-Laronde camp. So this is located in the Abitibi sub-province, very close to the Cadillac-Lauder Lake fault, which is a major regional deformation zone. And the district is right to the north of it. And there's a really strong foliation that's east-west subvertical that's overprinting all the volcanic rocks and the VMS deposits. And when you look at it at a smaller scale, you can see there's this very strong foliation that has overprinted the rock. So everything has been transposed completely parallel to this foliation. And a really good example is to look at both the massive sulfide lenses and their stringer zones. So if we remember the initial model, the massive sulfides are subparallel to the seafloor. They're conformable, and the feeder zones they are at an angle because they're following scene volcanic faults. So that's the expected geometry. But after transposition, everything has been parallelized to the foliation, and you end up with, here in red, that's the massive sulfide zone, and the blues are the garnet enrichment zones. So this is the alteration that's related to the hydrothermal fluid going up. And again, this is forming zones that are subparallel to the massive sulfide lenses. Everything has been completely transposed, flat. We only have a pancake left. So initial geometry, again, completely destroyed, and we're left with the effect of the final deformation event that's controlling the final geometry of the deposit. Another interesting effect of deformation, that's boudinage. So boudinage can overprint mineralization in VMS systems. This is typically due to the fact that there's a lot of competency contrasts within VMS deposits. The sulfides are generally more ductile than their host rocks, at the exception of pyrite, which is a little bit more competent. So they'll tend to behave more like toothpaste relative to the host rocks. And the same thing happens for the alteration zones. Chlorite, sericite, compared to a basalt or rhyolite, these are very incompetent rocks. They'll tend to deform in a ductile manner, while the surrounding host rocks will be more brittle. And you'll end up with a lot of boudinage. Here's a few examples. So right here, this is in the Iberian Pyrite Belt, where you have boudinage, chalcopyrite, and pyrite within a matrix of galena and sphalerite right here. Another example, so these two examples are from the Lalor deposit. Here you have a mafic dike. So again, the more competent rock that has undergone the deformation by forming boudins. And within the necks of the boudins, you have the massive sulfides that have been injected in the necks. And at the tip of the neck of the boudin, you'll have quartz veins forming. The same thing right here. You have a smaller mafic dike that has broken in a brittle manner. And within the boudin neck, you have galena quartz biotite, so more metasomatic recrystallization that's happening. Another effect of deformation on sulfide deposits, that's mullions. Mullions or piercement structures, they are formed by the injection or projection of ductile sulfides in the wall rock. So you can see it as the effect of folding on a ductile rock. One really good example right here, you have a pyrrhotite chalcopyrite vein that was initially at an angle to the deformation. So you can see the foliation that's oriented roughly like that. And with the transposition, the sulfides started to fold. And at the hinges of the fold, they started to be injected within the wall rock, forming these injections parallel to the foliation. Here's an example, this one at an angle of the foliation, where you have massive sulfides with pyrite, sphalerite, and the more ductile pyrrhotite that's injected within the wall rock. So you'll tell me, well, this is at the scale of just 1 meter. It doesn't matter that much on the final geometry of the deposit. Here's a deposit scale example on the Lalor deposit, where you have The brighter color, this is the hydrothermally altered rocks with the outline of the sulfide mineralization, massive sulfides in red. And you can see that you have host rocks around it that are not affected by alteration, so they are a lot more competent. And during the deformation, that was a compression roughly like that, so compression following the laser of my pointer. You started to fold, and then you had injections through mullions of both the ductile alteration zones and the massive sulfides. And this is at the scale. If you look at the scale right here, this is more than 100 meters of injection of the sulfide lenses. So the final geometry is highly controlled by these mullions, and there's a remobilization at a scale of tens, if not hundreds of meters of the sulfides. So our plunge in relation to overprinting high strains, what happens when you have higher and higher strain is that you'll tend to have a rotation both of the plane, so like we've seen in a transposition, but also of the plunge of the mineralization. So at lower strains, what's going to happen is that our ore is going to be affected by folding. So as we've discussed, the ore is going to follow the hinges of our fold, so it's going to be perpendicular to our compression orientation. But with more intensity of the deformation, you'll have a progressive rotation of both the fold hinges and the plunge of the mineralization to end up parallel to the compression orientation. And there's a really good example, which is the K-Mine deposit. So this one is in Arizona. This is a historical VMS deposit that's been initially mined a while ago, but there's more exploration ongoing at the moment. That's located within a thin metamorphic and strongly deformed volcanic belt. So if you look at this geological map, everything in brown and pink, these are intrusive rocks, and the green and the blue-green colors, these are the sedimentary and volcanic rocks that are pinched in between these plutons. And what happens is that because of the presence of these two plutons, it's being completely squeezed. There is a very, very strong deformation event that has linked to this rotation of the lineation. So if we observe at surface in outcrop the different structural features, we have a main foliation that's affecting the bedding here in sedimentary rocks. It's north-south, so subvertical north-south foliation. You have a lineation, mineral lineation right here, that's along down dip of the foliation. And you have folds. So interestingly, these folds, they have north-south axial planes subparallel to the foliation, and they have fold hinges that are subparallel to the lineation. So we can see exactly what I described before. Our folds have hinges that are down dip instead of being horizontal, and they follow the lineation. They have been rotated subparallel to the lineation with the intensity of the deformation. So if we look at all these observations, what would be the expected plunge of the mineralization of a VMS deposit regionally? So the VMS deposit has rotated subparallel to the main lineation. So by measuring this mineral lineation, we're able to predict the geometry of an expected VMS deposit. It's going to be transposed subparallel to this foliation and plunging along this lineation. And lo and behold, that's exactly what the deposit looks like, where you have in a map view, so from the top, you have the lens that is roughly subparallel to the foliation. So this is the north is to the right, the south is to the left. It's forming a lens, a north-south lens. But when you look in detail, the drill hole intersections, it's actually a repetition. You have a folding of the lens with a repetition here and nothing in between. And the hinge of the fold that we can see in this view right here, it's down plunge of the main foliation. So just by looking at the different outcrops, looking at the structural features, you're able to predict the geometry of the deposit. So the important point is that The final geometry of the deposit, what we observe right now, it's completely due to deformation. It doesn't represent the initial structural controls. Thin volcanic structural controls is completely due to the final deformation events that have completely remobilized the VMS system. And again, to illustrate this point, this figure that shows the effect of increasing strain, where you have an unstrained rock with generally no fold, with initial strain, my strain, you'll have folds with a shallowly plunging fold hinge, weak lineation, and with the more intense deformation being stronger and stronger, you'll have a rotation of the fold hinges along the lineation and complete transposition of your deposit. Now the deformation of massive sulfide bodies and within the body itself. So VMS and other sulfides deposits generally include deformation and remobilization. There's three main types of remobilization that I want to address here. There's the solid state or mechanical remobilization, and we've already seen a little bit of that through boudinage, folding, mullions. So in this case, the sulfide are remobilized in as solids. They behave a little bit like toothpaste, but you can also have liquid state remobilization, where the metals will be dissolved within a metamorphic fluid. They'll move around and then they'll redeposit somewhere else. And there's sulfide anatexis, which is remelting of the sulfides. Sulfide minerals, sulfosols, telluride, minerals like that, they don't need as high temperature as silicates for melting. And at temperatures like green schist, upper green schist, and amphibolite, you can already start to melt them, which facilitates the remobilization. So I'll show some examples of that. Well, first example here is within a boudin, or an illustration of within a boudin of massive sulfides. We have the remobilized ore that's at the edges of the boudin by mechanical remobilization. One important point about remobilization is the scale. Remobilization of sulfides and metals can occur at the scale of millimeters up to hundreds of meters. And here's an example right here where you have a pyrite grain with a trail of gold that's been remobilized, exhaled from the pyrite, and that's forming a gold grain right here. The important point is that remobilization can have an impact on deposits, both on the geometry and for geometrological purposes. If it's at the scale of millimeters, it's not going to affect the final geometry of your deposit, might affect recovery, for example, but not as important for exploration. So not all remobilization is significant for deposit economic. So the solid state remobilization, most sulfides have a ductile behavior in conditions where silicates would have a brittle behavior. And I already mentioned that. They behave a little bit like toothpaste. So this diagram shows, so for example, on the left, this is the boundary between brittle and ductile behavior for different sulfides. You see galena right here, sphalerite, pyrrhotite, chalcopyrite. And even before you reach the zeolite metamorphic fascias, you already have ductile behavior for these sulfides. It's only there's... Okay, I'll put that on the side. Hopefully everyone is still connected. The pyrite has a behavior that's more similar to that of silicates, where it's going to be behaving in a brittle fashion up to the green schist amphibolite fascias. Sorry. Here's a really good example where chalcopyrite has already reached its ductile behavior temperature, while sphalerite hasn't. So in this sample, you can see that the zone with more chalcopyrite has a very strong foliation. There's ductile deformation. You have a porphyroclast with a recrystallized mantle that's indicating a strained shadow right here. So complete ductile deformation. And right next to it, you have a band of sphalerite, which has a brittle deformation features. They are shear fractures, so it's the equivalent of boudinage, but in a brittle manner. And you can see a rotation of the brittle fractures. So both the ductile and the brittle deformation indicate what would be a normal movement on this image. and just because of the different behavior at different temperatures, you'll have different structural features. Here's a really good example of a ductile remobilization or mechanical remobilization. This is the Magdalena deposit in Spain. And you can see that the geometry of the deposit is cross-cutting the volcanic stratigraphy. So you have the contact between a mafic and a felsic unit right here. You can see that the mineralization is cross-cutting this contact. And within the zone itself, there's very intense shearing, and the initial metal zonation is completely lost in this case. When you look at the deformation within the rocks, you see very intense deformation, very intense foliation. You have fish hook folds, which are really good examples of strong folding and transposition, so really intense deformation. And you have a banding between pyrite chalcopyrite and sphalerite galena zones. One interesting observation in this case is that observing the plunge of jasper boudins and folds within the sulfides, you can measure the plunge or the overall structural stretching orientation, and this is parallel to the lens itself. So again, the geometry, the final geometry of the deposit in this case is controlled by the orientation of the stretching lineation, so by the deformation within the shear zone that hosts the mineralization within this lens. While at the top right here, you have this other lens. So I should have mentioned it before. Right here, you have this lens, which is this time subparallel to the stratigraphy. And this one, the zonation has been preserved. You have the zinc and lead rich at the top, the copper at the bottom. There's a lot less deformation. So this one has not been remobilized, and it has preserved its primary geometry because it's not within the shear zone cross-cutting the volcanic stratigraphy. After the mechanical remobilization, the liquid state remobilization. So this example is at the Lalor deposit, and sulfides can be dissolved and remobilized by metamorphic fluids. So what happens is that within a massive sulfide deposit, you have a lot of rocks or minerals that have fluids in it. You have the cerussite and chlorite, it's rich in water. You have the carbonates, it's rich in CO2. You have the sulfides, themselves rich in sulfur. So with metamorphism, you have desulfidation, decarbonation, dehydration. You'll form a lot of metamorphic fluids that will have the potential to leach some of the metals. And this is a really good example where you have a transition between a mechanical remobilization. So you have here on the right, a massive sulfide lens with mechanical remobilization as mullions and piercement structures of the sulfides. And there's a transition. So you have right here, massive sulfides being remobilized. You have clasts of the wall rock that are rotated. You can see the foliation is rotated within the different clasts. And then you have a transition. So right here, you can see there's a zoom in right here, where you have a transition from sulfides to something that's quartz sulfide veins. So something that has already a little bit of metasomatic fluids involved. Here another zoom in where you have a transition to quartz actinolite galena veins. So in this case, this is a recrystallization of a metasomatic fluid. It's not mechanical remobilization anymore. And at a more distal, you have a pervasive alteration. So here's a photo of it, of calcium-rich metasomatism, enriched in precious metals and poor in sulfides. So you have actinolite, chlorite, and some sulfides, but compared to massive sulfide, it's really poor in sulfides. And this is a really high gold-rich zone. This is in the several grams per ton gold. So here you have it at the scale of a few meters. But the really cool thing is that this occurs at deposit scale. So in the case of the Lalor deposit, you have in this cross-section, in blue, you have the massive sulfide lenses, which have been folded. You can see the fold repetition right here. And you have these zones here in yellow of gold-rich lenses. These are our calcium-rich metasomatism zones, very poor in sulfides, very rich in gold. And you can link this gold to being remobilized from the massive sulfides. So in this case, it has been refocused, forming additional zones, so it's still economical. But you have also examples around these massive sulfide zones where there's diffuse enrichment in gold that's below economic grade. So in this case, you have like remobilize the element and making it less economical. So in this drill hole, you see a little bit of an example of that, where you have a massive sulfide zone rich in iron, zinc, copper, and then you have zones enriched in gold right here below. So gold, silver, very low iron, meaning there's not much pyrite, very low zinc, a little bit of copper, but definitely a sulfide poor zone. But when you look at the gold grade, that's pretty high. Same thing happens here, for example, where you have an association of gold, silver, lead, very low iron, so very low sulfide, low zinc, low copper, forming distinct zones. The final type of remobilization, this one is more anecdotal, at least that's why I think. I've never seen it forming remobilization at more than a few millimeters or centimeters. This is sulfide anatexis. So as I mentioned, some sulfide minerals can melt at medium to low metamorphic grades, green schist and amphibolite facies. It happens that it tends not to be the copper, the zincs, or the lead, but more precious metals, molybdenum, silver, gold tend to be incorporated within these melts, tellurium, arsenic, antimony. So this can lead to the remobilization of sulfides. It's been documented in several deposits, so Broken Hill, Montauban, and the Lalor deposit, for example, where you have this very nice recrystallization, but that's at the scale of a thin section, so interesting for the sake of science, but not so much interesting for exploration. Yeah, so the conclusions, VMS deposits form in regional or local extensional settings. They're strongly controlled in their geometry and location, often placement by the synvolcanic faults and the volcanic architecture. So the initial geometry is strongly controlled by the structural setting at the time of the emplacement. But the issue is that the VMS deposits currently at surface have generally undergone some level of compression. There's been an inversion. Sometimes it's complex, sometimes it's polyphase deformation. It can be really intense. So their geometry can be strongly controlled by lateral deformation and sulfide remobilization. So this deformation can obscure the primary structure, and sometimes the geometry we observed is mainly controlled by what happened after the deposition rather than the scene deposition environment. So we need to understand what happened during deformation to understand the current geometry of deposits. And I wanted to finish with this image, which I think illustrates really well what can happen to a VMS deposit. So this is a perlite or spherulite texture within a rhyolite in the Iberian Pyrite Belt. So this texture, they are supposed to be small bubbles in the rock. And when you look at this face of the outcrop, yeah, it's a lot of small bubbles in the outcrop. Well, when you look at this other face of the outcrop, everything has been completely elongated, completely stretched. They are extremely stretched cigars. And you can imagine that if you can do that to a rhyolite, what can you do to a VMS deposit that's completely ductile? Yeah, that's it. I don't know how I did in terms of time.
Oh, you're doing great.
And yeah, acknowledgement. So I'd like to thank our clients who were okay for us to show some results. So yeah.
Yeah, thank you, Antoine. Excellent presentation. Congratulations. Very good work. And I guess this was based on the workshop you gave at PDAC.
Correct? Yeah, it's some material from the workshop.
So keep your eyes peeled for another workshop being offered at PDAC. Not this year, not the coming PM conference, but the conference after, I think. Yeah, so we're happy to take questions from the audience, and maybe to kick things off, I was wondering if you could comment on gold-rich VMS deposits. I'm thinking of La Ronde, and I'm thinking, you know, is it really the original magmatic environment that drove that gold enrichment, or do you think it's secondary processes like the ones you mentioned?
So, okay, yeah, that's a complex question. Actually, researchers don't necessarily all agree on what happened for gold enrichment in VMS deposits. There's several factors. There's one which can be geodynamical. If you form volcanic rocks that are more rich in gold, then if you leach them, you'll have a VMS deposit that's more enriched in gold, and then it's going to be at the district scale. All your VMS deposits at the district scale will be more enriched in gold. An example would be probably at the Snow Lake district, where a lot of the deposits are enriched in gold. Another possibility is enrichment through the contribution of magmatic fluid. So what I discussed initially is that the overall concept of VMS system is that the magmatic chamber at depth only contributes heat. But in some cases, it can also contribute fluids. And in this case, you can have an enrichment in gold from these magmatic fluids. An example would be the SK Creek deposit, which is a transition between epithermal and VMS deposit, or the Westwood deposit in La Ronde, actually, in the Doyon-Bousquet-La Ronde camp, where there is a very good documentation, I think, of the contribution of a magmatic fluid to the VMS deposit. Another way to enrich in gold, this is through what's the term? Ebullition. So if the VMS deposit, and this one is more theoretical, like I've never seen an example that convinced me it was possible, but I'll mention it nonetheless. If the VMS deposit forms in water that's not too deep, there's the possibility that the pressure is not strong enough, and because it's a very hot hydrothermal fluid, it'll be able to boil. When it's boiling, you'll have a differentiation. If I remember correctly, the chloride, so Cl-rich part of the fluid will have most of the base metals, and then you'll have the gold that's going to go the other way with the hydrogen-rich part of the fluid. So I think that's the boiled part, so the vapor phase. Don't quote me on that. I don't remember. I don't remember for sure. But yeah, there'll be a differentiation, and you might be to enrich gold this way. And then finally, with metamorphism and deformation, you can have re-enrichment. The example being the Lalor deposit, where you form gold-rich zones by remobilization. So yeah, it's a relatively complex subject. Yeah.
Yeah, happy to take any other questions.
Have you had a chance to ever look in your work at some magmatic deposits, which are highly metamorphosed, which undergo the same sort of treatment, which are in terms of post-depositional magmatic sulfide deformation and immobilization? Have you seen nickel copper magnetic deposits that could have undergone this sort of interpretation as well?
So for the audience on the internet, so the question is have I ever seen nickel copper magmatic deposits, which are also sulfide-rich deposits that sometimes undergo a lot of deformation? Unfortunately, no. So I've read a lot about them to compare with the deformation of VMS, but I've never had the opportunity to actually go in the field and work on such deposits. I would be really curious to see the. I'll be really curious to because in theory they would be the same type of remobilization and structures that we observe in VMS deposit.
I'm thinking of the Ferguson Lake deposit up in the middle of it, highly metamorphosed, and you get these very rich plugs in other areas where they're attenuated, and areas which are very high in PGEs.
Okay, so it would be interesting to see regionally what's the geometry of the faults, what's the lineation regionally, and see how it fits with that. Yeah.
Several online questions, so if you just repeat it for the benefit of the online people. Okay, so Kuroko deposits in northern Honshu form on the seafloor upon continental crust at a change in regional stress regime where there has been a coeval change in eruptive magma composition. Have similar changes in stress and volcanism been identified in other VHMS deposits? I am sorry if you commented already on this and I missed.
That's a really good point. There's good examples where you see a strong change in the volcanism and the magmatic affinity of the magmatism at the from the footwall to the hanging wall of VMS deposit. So I'll comment on the Snow Lake district, which I know better or know well, where you have a transition from a more calcaline, more mature arc composition of the volcanic rocks in the footwall, and immediately in the hanging wall, you have a transition to mafic rocks that are a little bit more like still calcareous toward the tholeiitic, that are interpreted to illustrate a change from a mature arc to arc rifting. So a transition from mature arc to arc rifting. So that's another example. And yeah, there are other examples like that. So this is more possible to interpret that with the geochemistry of the host rocks. Yeah.
Okay, and another one here. Is it possible to give a good example of big VMS deposits in advanced exploration stage and development stage? Thank you so much. And can you just repeat the question?
Okay, so the question is there examples of big VMS deposits that are currently being developed or mined? Is it?
In advanced exploration stage and development stage. So
advanced exploration and development stage. Yeah, there's I think the Arctic deposit in Alaska is relatively, I don't remember the size, but I think it's relatively big. There's deposits being redeveloped, like the Horn deposit. It's a major deposit being redeveloped at the moment.
There's Nexus Aripuana in Brazil.
Yeah,
That's
Aripuana
being developed.
Yeah. Which is in high grade metamorphic rocks. Yeah.
Castellano would be the Castellanos. Cuba.
Okay. I don't know about this one.
I worked on this project
So,
a few years ago.
Castellanos in Cuba. Okay.
Yes.
Okay.
Peñal del Río in Cuba.
Yeah, nothing that can think of.
Red Dog in Alaska, but the mine is inactivated.
Oh, Red Dog?
Yes,
It's I think Red Dog isn't it an MVT or SEDEX? Yeah, SEDEX. Yeah.
or perhaps the Julimar in Western Australia, which is a huge magnetic
Yeah.
deposit being developed, and it's been highly remote.
Yeah, a recent discovery. Yeah. There's also the McIlvenna Bay in Manitoba, which is what was the size? I think relative 20 million tons. Saskatchewan. Oh, sorry. Yeah, right next to the border. It's in Saskatchewan. 20 million ton, which is relatively big for VMS. Like without being huge, it's relatively big. So yeah, there are still discoveries being made nowadays. Yeah.
Any more from the audience? There's lots more online.
I had a quick one for the K deposit. How did you figure out that it's internally folded? Did you see that classic zonation in terms of metals that you
Yeah, that's a really good point. Yeah, it's yeah, here you go. So the color you see here, this is based on the metal. Oh, can I zoom in? Probably. Yeah, here you go. Yeah, here you go. So what I did is using a clustering algorithm, I divided the mineralization in different composition, and you can see all this is you can see it still pretty well. You can see there's domination. It's dominated by zinc lead on the outside and by copper and zinc lead copper on the inside. So you can see there's a structural repetition right here. There's also the fact that you have altered rocks at the core, and the hanging wall and footwall are unaltered. So that suggests that you have the stratigraphic hanging wall of the deposit is both in the hanging wall and the footwall of the current lens.
Okay, another one online. Great talk, thank you, Antoine. You mentioned the post-folding Sturgeon Lake fault. The papers from that area make an argument that these straight faults are bounding VMS mineralization. Isn't that contradictory to your thesis that sulfide mineralization formed before folding? And can you just repeat it from?
Yeah, so the example is from this image where there's the paper. So I guess that's from Galley or Franklin, I don't remember, where VMS are bounded by these faults. So yeah, that's one observation. I would be I'm not familiar with this zone, so I can't comment anything for sure. But I would be careful looking at the geometry of this deposit, saying the deposits are bounded by these faults. Maybe is it fault controlling the distribution of these deposits? That's another question, and it would be interesting to see more detailed mapping about that. But I would be always careful looking at faults that are perpendicular to the deformation grain that seem to offset in a brittle fashion the stratigraphy, because it's unlikely they would be synvolcanic faults that would have been preserved. Yeah.
Okay, and have you looked at the remobilization of critical elements within VMS deposits? And just repeat the question for the.
So I looked at the remobilization of critical elements within VMS deposits. So I'm not too familiar with it. So gold, yes, I'm familiar with it, but other elements, not at all. So I can't really comment on that.
Probably do one more, so we can have beer. Yeah.
Okay, I'm gonna pick my favorite one then. Well, I'll just look at it. Can you please repeat the depositional environment of the last photo you said were gas bubbles? And then the second part of this question, can you trace the depth of the bubble source? And if not, what are the changes of this being trace fossil? Chances of this being trace fossil? They look like Heliophycus.
Okay, I don't understand. So yeah, I think it refers to the ebullition and the split between the enrichment in gold within the vapor phase. So I don't remember exactly the details of this model, so I don't want to comment too much on that. I can send so good papers to read about that. I forgot the name of the authors, but if you send me an email, I would be able to send good papers describing that in more detail by people who know a lot more than me about that. Yeah.
All right, last chance for a question from the room. Any pressing questions? No? Well then, thank you so much, Antoine, for patiently answering all the questions, and great talk again. Thank you. And this is the last talk of the season today. So we will hopefully see you all in September for our next round of TGDG talks. And if you have any suggestions for talks, or you would like to present yourself, feel free to send us an email through the website. We're always happy to have interesting geological talks. Today's reception is sponsored by SRK, so thanks to SRK, and acknowledging our sponsors who are basically the companies that the volunteers work for, and we're volunteering our time here. So Ellie Owens here in the room with E2 Gold is right now volunteering, and myself, I work for SLR Consulting. And these are the other committee members there. So thank you very much, and let's go head over to the reception, which is just outside the room. Thank you. Sharing.